Hello, my name is Don Metzger. This video is about the Analog Devices ADRV9002 transceiver chip running with a Xilinx AMD ZCU102 host board under Analog Devices IIO software, and we'll be doing the evaluation and demonstration using qIQ Systems qIQ Transceiver software. Here's an overview of the video. We'll be starting with a description of the measurement setup showing the boards and their relationship. Then we'll be creating an SD card image to boot the ZCU102 board. Then we'll show you how to verify that SD card image using a terminal connection. Then we'll move on to running the system using qIQ Transceiver software. Then we'll show you how to make your own profile using the TES software from Analog Devices. And then finally we'll run that made-up profile using qIQ Transceiver. Here's our measurement setup. The big board at the top is the Xilinx AMD ZCU102 board, and then the smaller board at the bottom is the ADRV9002 eval board. There are two FMC slots to choose from. The correct one to use is the one on the right. The ZCU102 has an SD card up on the top left. It's also got an Ethernet connection. We're going to just use a loopback cable from transmit channel number 1 to receive channel number 2, and we're using receive channel number 2, the A port. As always, it's a good idea to blow a little air across the system just to keep things cool. Alright, so the first thing that we want to do is make a bootable SD card image for the ZCU102 board. So I'm going to plug in my SD card writer, and the software that I like to use is Win32 Disk Imager, or the image writer. So first of all, we go and choose the image that we have downloaded from Analog Devices. So this is the latest at the time of this video, and then we're just going to write it to that SD card, and then we click the write operation. This might take a while, maybe around 10 minutes, 7 minutes, hard to say. Anyway, see you at the other end of this process. Alright, so now we're done writing the SD card. Now we need to go in and configure it for the ZCU102 and the ADRV9002. So we go, and sometimes Windows doesn't like the partitions that are on there. So we're presented with a whole bunch of different host board and eval board setups. So the ZCU102 is a Zinc multiprocessor, so we go into the common there and copy that image file, and then we go back to that root and we paste it in at the root level of that SD card image. Then we have to go find our board that we're using. So we're doing a Zinc MP ZCU102, and we're looking down through here, and there's our 9002 directory. And then in there you've got more choices yet to make about how to configure this. Let's start with the LVDS versus CMOS. This is a faster way of getting data in and out of the chip, the LVDS method. CMOS is a lower power method, but it can't run quite the speed. So we want to use this. So we go in there and we take boot.bin, copy that, and put that in the root of the SD card. And then we go back and find that folder one more time. Zinc MP. Okay, so back in the directory there are two other folders to choose from. This is known as the independent mode, and this is known as the MIMO mode. Why they're not marked independent and MIMO, I have no idea. But we want to go into this one and take our system device tree and copy that and put that into our root directory. Alright, so we have now created the bootable SD card image for the ZCU102 board. Okay, so now we want to verify that the SD card image boots and works. So we've booted up the system, and I'm going to do a terminal connection using PuTTY to the ZCU102 board. So I've hooked up a USB cable, and I've got the Silicon Labs driver installed on this computer. And you want to look for the lowest numbered interface, and remember that that's COM7. So this is in the device manager for Windows. So COM7. So now I bring up PuTTY, and we're going to do a serial connection through COM7 at a speed of 115/400, and do that connection, and there we are. Let's make the window a little bit bigger here so we can have it show us more information. So you don't need a password or username when you come in through the serial port connection. If you do an SSH connection, then you'll need the password, and for root is analog. I'm just going to do IIO_info. This is a little Linux computer running inside the ZCU102, and IIO_info is going to dump a whole lot of information to us, and it's telling us about all the IIO devices that it found out there. So I'm going to scroll back up a little bit, and as long as it's finding this AXI ADRV9002 TX2 LPC devices like that, then you know that everything is good and your board is ready to go. If it doesn't show this, maybe you're in the wrong FMC slot, maybe there's something wrong with the eval board. There are multiple things that might be wrong at that point. Alright, another thing we want to do while we're here at the terminal connection is ask it for the IP address that it has on the network. If you're doing DHCP on your network to assign different IP addresses, you need to find out what's been assigned to that. And so here we are right up here, 192.168.0.29 is the IP address that got assigned to this particular board. Alright, so let's minimize this window. You can close it or just minimize it, and let's bring up qIQ Transceiver software so we can run some waveforms through the device. For instrument, we want to make sure that we're telling it it's an ADRV9002. We're going to access it using IIO over the network, and it's at this IP address, which is the one we got for the ZCU102 board. Then we want to go down to the ADRV9002 control dialog, and we want to make sure that we're transmitting out channel 1 as we are, and you can choose some frequency. I just chose 500 megahertz and some amount of attenuation on the transmit side. Then on the receive side we'll be coming in channel 2. The RXA is what's connected on the board. The center frequency, same, 500 megahertz, manual gain control. I'm going to start with a gain value of 25 dB, and I'm going to capture 30,000 samples. Finally, down here we have included with qIQ Transceiver software some built-in profiles. So we've got some LTE related sample rates at 15.36, 30.72, 61.44 megasamples per second. We're going to be running the 40 megasample per second mode, and then there's also a user defined that we'll get to later in the video. So we're going to run the 40 megasample per second mode, and now we go and choose a transmit file. For this particular demonstration, I'm going to run an 802.11a signal through the system, and so we have already made that waveform using QIQ Generator, and it's an 802.11 with 12 megabit per second and 40 OFDM symbols per frame. Then we go up here and we hit start. The first thing that happens down here in the status bar, you'll see that it's setting the profile. We always set the profile before a run begins, so we know what state the chip is in. So we are transmitting and we are receiving an 802.11 OFDM type signal using the ADRV9002. Just to make this a little less annoying, I'm just going to stop it here. So in the top left hand corner, this is the time domain view of the data that is acquired. So it says acquired waveform. And we're just looking at power versus time. Then we take all of this and do an average spectrum, and so that's called the acquired spectrum. And then this data right here is the acquired spectrogram. So joint time frequency, look at the data. Frequency is horizontal and time plays out from the bottom up to the top. And when we do a demod for 802.11, we go in and capture one of these frames. So we have to trigger and search through the data and find a frame. So here we looked through the data and we found a frame of data to process, and this is the spectrum of that data that we are actually going to process and do the demod on. So the windows are named Processing Waveform and Processing Spectrum. Then we go through the whole demod of this. We sync up with the short training sequences and the long training sequences and figure out what's in the packet and go through the packet OFDM symbol by OFDM symbol, and we demod it and we end up with a QPSK constellation, because 802.11 for a bit rate of 12 megabit per second uses QPSK modulation type for each of the subcarriers. And so there's information over here about the type of waveform that we are processing, and then we also provide an OFDM EVM plot. So this is EVM by subcarrier as we go across the bandwidth of the signal for each of the subcarriers, and we're plotting the average and the max. And then we also provide just one number that is the overall EVM for the 802.11 signal. If we were to run a different bit rate, 1836, there are other bit rates, that would create different modulation type of symbols that would be on each of the subcarriers. But if 802.11 is not the waveform of interest for your application, we handle many other different waveform types, including demodulation. We also change the mode of the chip through the profiles. We've created a few profiles, but the 9002 chip has a lot of different ways in which the chip can be configured. So let me show you how to create a user profile that you can put the chip in a different mode than one of the profiles that we supply. In order to create a profile, we use the TES software from Analog Devices. So I'll bring that up, and we're not going to connect to the device. We just want to go over here to device configuration and use this software to create a profile for us. So we want to make sure we're doing the right chip, 9002. I prefer the FDD mode, frequency domain duplex. Let's put this in a custom setup, dual channel. I prefer my frequency units in megahertz. Now all I'm going to do is to create a 20 megasample per second mode, because we don't have one of those, and maybe that's more efficient for what you would want to do. So we just go down here and type in 20 megasamples per second. Let's say it's maybe 12 megahertz bandwidth, and we want to make sure also that the TX is doing 20 megasamples a second and a 12 megahertz usable bandwidth there. And there we go, we got these other channels doing the same thing. There's a whole lot of things that you can do to configure the 9002 and put it in all sorts of different states. This software is just focused on the chip. So the eval board has certain firmware, it has certain device trees that we loaded. So for instance, you remember we loaded the LVDS device tree. If I went in there and changed this to CMOS at this point, that's inconsistent with the firmware and the device tree that we loaded for this. So you have to be careful in here. You're not free to choose everything you want. You have to be consistent with the way the firmware and the SD card boot image is expecting to see the chip. But there's a lot of things that you can change in here. When we get this the way we want to, go up to the top, check that we're in a valid state, and let's just go generate the profile file, and I'm just going to go save that in some temporary place, and this is going to be a JSON file, and I'm going to give it the name ADRV9002 underscore user dot JSON. And then there's another file that we have to create, and that's the stream image. And again, let's go to that same location and say this is the ADRV 9002 underscore user dot stream or stream. Okay, so now we have created a new JSON and stream file associated with this way of using the chip. One last thing that you need to do is when the TES software stored the ADRV9002 underscore user dot stream file, it actually stores it as a .stream.bin. So you need to go into here and rename this just .stream. And Windows will say, "You sure you want to do that?" And we go, "Yes, we do." So that's one of the things that we need to do, so that now we have ADRV9002 user.json, ADRV9002 user.stream. Now we need to take those two files that we've created with the information about the profile and make them accessible to the qIQ Transceiver software. So on your install, you should have been put into a qIQ Tools folder, and then inside there you'll see a qIQ Transceiver folder. Go into the qIQ Transceiver folder and then go into baseband. Baseband has all of our profiles and configurations, baseband configurations for some of the other chips. In there you're going to find the ADRV9002 user.json, ADRV9002 user.stream. Just replace those files with the profile that you just generated, and that will make them accessible to the software when we start up again. Okay, back in qIQ Transceiver, let's go to the instrument settings for the 9002. And in there, we'll leave all the settings alone, except for the configuration, which we will set to user-defined. That'll use that profile, the user profile that we just created. Alright, now we need a transmit file that has not 40 megasamples per second, but something more like 20 megasamples a second. So I just happen to have such a file. There should be a 16 QAM and 4 megasymbols a second with a 20 mega sample per second. Here we go, 16 QAM, 4 megasymbols a second. We made this using quick generator software. Then I'm going to uncheck this box here so the software doesn't try to set the profile automatically. So let me go over here. We want to select PSK on the toolbar, and up here we want to select PSK QAM. We want 16 QAM at 4 megasymbols a second, and let's turn on some corrections for DC offset and IQ imbalance. Alright, so now we're ready to go. We just go over here and hit start. Again, it always starts with the setting of the profile. And now we're up and running. And here's our 16 QAM waveform running at a 20 megasample per second rate with that user profile that we just created. Alright, so that's how you can use the software to create your own state for the chip and run it in whatever mode you would like to use it in. Alright, that's it for this video. You can always visit us online at qIQsystems.com or send us an email at sales@qIQsystems.com. Have a good day.